Welcome back to this video series on capacitors in electric circuits. I'm Mr. Gal with Get Ahead Learning, and in this video we are going to focus on capacitors in series. If you ever feel so inclined, then be so kind to give a thumbs up, subscribe, and or hit that notification bell. I'm not going to stop you, and I do appreciate it. So, without further ado, let's get ahead. In my last video, I explained and described the physical construct of a capacitor. I highlighted some of the various functions a capacitor may be used for within a circuit, and I walked you through the charging process of a single capacitor when it's hooked up to a battery. Now, the objectives that we're going to hit on in this video include understand how to determine if capacitors are in series. We will then derive the 3 rules for capacitors in series, including the charge stored, the voltage across, and the effect of capacitance. And to keep the length of this video reasonable, I'm going to solve problems involving capacitors in series in follow-up videos, as well as address the objectives below. So let's get to it. All right, so we know capacitors may perform different functions, and it's important to be able to control its effect on the circuit. Understanding the manner in which capacitors are connected to each other and its net result is crucial to building a working circuit. One way to orient capacitors is called in series. So what does it mean to be in series? Electric components are considered in series when they are connected one after the other. The wire connecting devices is a single pathway. Let's take these 3 capacitors, the battery, and some wire, and let's see if we can connect them so that they are by definition in series. I think the simplest, most straightforward way to show you a circuit in series is just to take these 3 capacitors, put them all next to each other, one after the other. We will connect the battery's positive terminal to the first capacitor's positive terminal. From the first capacitor's negative terminal, we will go to the second capacitor's positive terminal, and then from its negative to the third capacitor's positive. And then from the third capacitor's negative terminal, we will go back to the battery's negative terminal. Let's follow that wire one more time. From the battery, we go to the first capacitor, then the second, then the third, and back to the battery again. The devices are connected one after the other, and the wire forms one pathway for the electrons to flow through. Here I put together a schematic drawing of what this circuit looks like. 2 parallel lines, a small and a large one, represent the power source, and the larger of the 2 gets the positive terminal, and the smaller of the 2 gets the negative terminal. 2 equally sized parallel lines represent a capacitor. The positive terminal is connected to the positive side of the battery, so we get a positive here, and a negative plate, if you will, a positive and a negative, and a positive and a negative again. Being able to draw and read schematics is an important skill set to strengthen. How about this second circuit? Would it be considered in series? Yes, it would. If we follow the wire from the battery to the first capacitor, and then the second, and then the third, and back to the battery again, the wires formed a single pathway. This would be series by definition. How about this third circuit? Would it be considered in series? No, not entirely. Let's follow the wire from the battery to the first capacitor, very much like the first 2 circuits that we saw. However, after the first capacitor, we see that the wire splits to 2 different pathways. One wire goes to the second capacitor, and a second different wire goes to the third capacitor. The devices weren't connected one after the other in a single pathway from beginning to end, so this circuit as a whole would not be considered in series. In fact, its schematic drawing would look something like this, in which we can clearly see it is not considered to be in series. Let's figure out the 3 rules for capacitors in series. First up, the charge rule. In the previous video, I walked through the process of a single capacitor charging when connected to a battery. We saw that electrons left one metal plate, traveled through metal wire to the positive terminal of a battery. The plate was less negative or positive, and in turn, attracted electrons towards it. These electrons essentially came from the battery's negative terminal, and ultimately, the end result was a capacitor with two charged plates of equal magnitude but opposite in sign. We will see the same process occur when charging more than one capacitor while in series. Electrons from the first capacitor's metal plate travels through the metal wire to the battery's positive terminal. What's left is a less negative or positive side to the capacitor, which in turn draws electrons towards it. But these electrons don't come from the battery's negative terminal, not yet at least. These electrons come from the next capacitor. This plate becomes negative, and this plate becomes positive, and the process repeats itself. Electron from the third capacitor is drawn towards the second. This plate becomes negative, this plate becomes positive, and then ultimately the last capacitor has electrons brought towards it from the battery's negative terminal. Ultimately, for every one electron that left one capacitor, another shifted over through the process. The charge that the first capacitor gained and lost was equal to the amount of charge that the second capacitor gained and lost, which was also equal to the amount of charge that the third capacitor gained and lost. Which brings us to our rule for charge for capacitors in series. We can say that the total charge, or the effective charge, is equal to the magnitude of the charge on the first capacitor, which is equal to the magnitude of the charge on the second capacitor, which is equal to the magnitude of charge on the third capacitor, and so on and so forth for however many capacitors there are in series. Let's answer this question. If the effective charge was 380 microcoulombs, and Q1 was also equal to 380 microcoulombs, what is the charge on capacitor 3? The rule for charge in series is that they are all the same, so capacitor 3 would also have 380 microcoulombs. Now let's figure out the voltage rule for capacitors in series. We will first do this experimentally, and then use the conservation of energy to explain the rule that we derived. First, let's hook up one capacitor to the power source. When we do so, we see that when the capacitor is fully charged, it holds a voltage across it the same as the power source. Now that we have the two capacitors next to each other in series, we can see that the voltage across the first capacitor of 2.56 volts plus the voltage across the second capacitor of 2.6 volts add up to equal the voltage of the power source. It looks like the rule for voltage for capacitors in series is that the individual capacitor's voltage adds up to be the voltage of the power source. Let's confirm that by adding a third capacitor and see if that trend holds up. When we put a third capacitor in series with the first two, as expected, their individual voltages added up to be the total of the power source. It should be noted that these capacitors, if they were truly identical to one and the other, then their voltages should be identical as well. However, the capacitors do have a tolerance of plus or minus 20%. So they really could range anywhere from 0.27 farads to 0.39 farads. Thus, you see the discrepancies in the voltages from one to the other. So in review, the effective voltage is equal to the sum of the individual voltages across each capacitor in series. In electric circuits, there's something known as Kirchhoff's loop rule. It's essentially electric circuits' version of the conservation of energy. Let me explain. Recall that we label the battery and the capacitors with both positive and negative terminals. We will move along the circuit, and every time we go from a negative to a positive, that will be a gain in voltage. Every time we go from a positive to a negative, that will be a loss of voltage, aka a voltage drop. For instance, if I were to start here on the wire, I first encounter the battery and I go from a negative to a positive. That would be a positive voltage. Next up, I come to the first capacitor. It goes from a positive to a negative. So that would be a voltage drop. The second capacitor would also be a voltage drop. The third capacitor would also be a voltage drop. And now that we have completed the circuit, we would say that needs to add up to be 0 according to Kirchhoff's loop rule. However, rearrange this, you're back to the rule that we found experimentally. Let's see if we can determine the voltage across the third capacitor. Given that the voltage across the battery is 1.5 volts, the first capacitor has 0.33 volts across it, and the second capacitor has 1.0 volts across it. The third capacitor must have a voltage of 0.17 volts. Let's recall the relationship between voltage, charge, and capacitance. The voltage is equal to the charge on a capacitor divided by its capacitance. This applies to not only the overall voltage, which would be equal to the overall charge divided by the effective capacitance, but that also applies to the individual capacitors as well. V1 would be equal to Q1 over C1, V2, Q2 over C2, and so on. If we were to rewrite the voltage rule in terms of charge and capacitance, all the Q's are the same and cancel out. What's left is the rule for the effective capacitance. Let's clean it up and take a look at it. The end result is 1 over the effective capacitance equals 1 over the first capacitance plus 1 over the second capacitance plus 1 over the third capacitance. But we don't want 1 over the effective capacitance. We want to know what is the effective capacitance. So after we add up the 1 over plus the 1 over plus the 1 over for however many capacitors there are, we're going to want to take the reciprocal of that. Now let's try a couple of examples. To properly use the capacitance rule for capacitors in series, we take 1 divided by the first capacitor of 300 microfarads, add that to 1 divided by the second capacitance of 300 microfarads, and add that to 1 divided by the third capacitance of 300 microfarads as well. That sums up to be 3 divided by 300 microfarads. Take the reciprocal of that, and we get 100 microfarads. Let's try another in which the capacitors have varied capacitance. We will go about this in the same manner, using different numbers. To find the effective capacitance, we will take 1 divided by 300 microfarads plus 1 divided by 600 microfarads plus 1 divided by 900 microfarads. Now 1 over 300 converts to 6 over 1800. 1 over 600 converts to 3 over 1800. And 1 over 900 converts to 2 over 1800. In total, we have 11 over 1800 microfarads. Taking the reciprocal of that, we get 164 microfarads as the effective capacitance. So in summary, we have that the charge of capacitors in series is all the same. The voltage across the capacitors in series add up to be the effective voltage. And lastly, we have the effective capacitance is equal to 1 over the first capacitor plus 1 over the second plus 1 over however many more capacitors there are, and we want to take the reciprocal of that. Wait, what's this? Oh man, it sure looks fun. Let's get ahead and solve this and more on the next video. Thank you so much for watching. Now the only thing left to do is give a thumbs up, subscribe, hit the notification bell. All right, till next time, let's get ahead.